So in this video, I want to go over the flowchart and model statement for Kery's example with a t-test with equal variances. We've got two populations, male, female falcons, and we're interested in their wing length. Comparing the wing length of male and female falcons with a t-test. And we'll begin, as always, with the flow chart, and we'll start at the bottom with the likelihood function right here. And what we're going to say is that the individual values of wing length are going to arise from a normal distribution that has a mean that we're going to refer to as mu I and some index of variability that we're going to call tau. Now, before going any deeper, I want to go over something we went over before, the distinction between the general linear model and the generalized linear model. And with the general linear model, we have this fixed component, mu I, that's determined like this. And then to get our observations, we start off with mu I and add some residual, where the residual comes from a normal distribution with mean 0 and standard deviation equal to sigma. And that's not what we're going to use. What we're going to use instead is a generalized linear model, which says that, once again, we're going to start off with mu I, the fixed component, but then we obtain our individual observations as random draws from a normal distribution that has mean equal to mu I and some standard deviation equal to sigma. So that's what we're showing here is the individual observations of wing length are going to come from a normal distribution with some mean mu I. What's this tau business all about? Well, perhaps regrettably, in JAGs, we don't parameterize the variability in a normal distribution either by sigma or by variance sigma squared. Rather, we parameterize the normal distribution's variability with this thing called tau that's represented symbol like that, where tau is equal to 1 over sigma squared, or obviously equivalent, sigma squared is equal to 1 over tau. So, in terms of the likelihood function, the observation is going to arise from a normal distribution with mean mu I, just shown down here, and this new thing tau, which is related to the more familiar variance in this way. So what we've shown here is that, just to reiterate, these values of y are going to come from normal distribution parameterized like this. And so what is mu I? Well, mu I is going to be equal to this strange looking beast here, B0 plus B1 times design. And so if this thing equals this thing, then I can just get rid of that and substitute in its place that thing. And so that's what I've done here. I've said that in terms of our likelihood function, the observed values of y, the observed values of wing length, are going to arise from a normal distribution that's going to have a mean that's going to be parameterized like this, and this odd metric of variability called tau. And so the obvious question is, what the heck is this? And so really what I want to do is spend a few moments trying to describe the rationale behind this. So remember what our data frame looks like. We've got 60 males, followed by 40 females, and these were the observed values of Y, the ones that we generated. Well, how did we generate these values of Y? We did it through a matrix operation. So we had this matrix here that I referred to as dummy that had 60 and 40. So it had 60 of these ones and zeros followed by 40 zeros and ones. So this is a 100 by 2 matrix. And then here we've got a 2 by 1 vector where this is the male wing length and this is the female wing length. And if you think about how matrix multiplication works, if we multiply this guy by this guy, what do we get? What we get is mu I. What we get is 107, 107, 107, 60 of those, followed by 40, 77.5, 77.5. And then what I'm going to, and before I go on, I should indicate that the observed values of Y start off with mu I and then add to it the residual, and we saw in the last video where they came from. We've got some code like this that's going to create something called design, which is a concatenation of two things. The number 1 repeated 60 times, followed by the number 0 repeated 40 times. So I can come back up here, and I can say we've got this thing called design. It's going to be 1, 1, 1, 60 of those, followed by 40 zeros. And now, what I can think about is this thing here. What is B0 plus B1 times design going to be? So I'm going to have B0 plus B1 times design. So, start off with B0. I better move this thing over here to make it a little bit clearer. There's my design. There's my mu I. B0 plus B1 times design, in this case, is going to be, we're going to start off with B0, and then we're going to take B1. We're going to multiply it by design. Well, design is this guy here, so you get B0 plus B1. Come down to the next row. You take B0, you add to it B1 multiplied by design. Design is 1, so you get B1, so forth, and so on. So that's okay for the first 60, correspond to the males. The last 40 that correspond to the females. Again, you start off with B0, I should say, and you add to it B1 multiplied by design. But because design in all of these cases is 0, B1 times design is also going to be 0, so you're just left with BO. So these are the values of B0 plus B1 times design. And here's what we see. What do we see is that B0 plus B1 is equal to 107, which is the expected wing length of the 60 males, whereas B0 is equal to 77.5, which is equal to the expected value of the 40 females. So now this thing hopefully is going to start to make some sense, is that if we parameterize our normal distribution with B0 and B1, that's going to be an adequate parameterization for our likelihood function. So let's look at the code. Actually, before that, let's look at our data. We're going to make this data like this. And so you're going to have values of Y, the observed values of wing length, that's going to consist of these 60 values here of male, and then these 40 values of female. We're going to have n sub the number of subjects, and then we're going to have design 61s and 40 females. What we're going to do is we're going to loop through n sub, which is 100. So we're going to loop through all those rows. And here's our likelihood function that says that the yi's are going to be derived from a normal distribution with mean mu I and tau. And we're saying that mu I is going to be equal to B0 plus B1 times design. So what's going to happen is once we implement this, we're going to wind up with posterior values for B0 and B1. But if we're going to get posteriors for B0 and B1, we're going to need to have their priors. And there are their priors there. They're coming from a normal distribution with mean 0 and tau equals 1 over 1,000. If you remember that sigma squared is equal to 1 over tau, a very small tau is equivalent to a very large sigma squared. So we've got very diffuse values for the priors for B0 and B1. We need to have our priors for tau. And again, just because of the way this works, we're going to assume that sigma is drawn from a uniform distribution. We then calculate 1 over sigma squared, and that's going to give us our tau. And at the end, what we're going to have are these two derived quantities. We're going to have these two derived quantities that says, okay, we're going to get the posterior distribution of B0 and B1. We saw here that B0 plus B1 is associated with the wing length of the males. B0 is associated with the wing length of the females. So we can say down here in our derived quantities that the female is going to be equal to B0 and the male is going to be equal to B0 plus B1. But probably the hardest thing to get our heads around is this idea of, it's shown right here, that we're going to have this alternative parameterization. We're going to think about the mean of the normal distribution from which our individual wing lengths are drawn is going to be given by this guy here. And so what we're trying to get are the posterior distributions of B0 and B1, because if we've got those, then we can get our female wing lengths as B0 and our male wing lengths as B0 plus B1.